The last thing to talk about when we talk about quadratic functions is projectile motion. So by the end of this lesson, you should be able to create a quadratic equation that models projectile motion, and then use that equation to find maximum height, the amount of time something is in the air, and the distance it has traveled. So when an object is thrown in the air, it's considered a projectile. The path of a projectile is a parabola if we forget about air resistance, which we're going to live in a perfect physics world for these problems where nothing affects the path of our ball besides gravity. So these problems use a function that represents an object's height, and it depends on three things. The force of gravity pulling it back down, which is always -16 if we're talking about feet per second. If you're talking about meters per second, when you get into physics class, that'll always be -4.9. The other things it depends on are initial velocity and the starting height. Initial velocity is how fast it was initially thrown or dropped or kicked. The initial height is how high it was when it was thrown or dropped or kicked. So these little zeros down here are called knots. So like V naught means the initial. And height, S naught, is the initial height for that. So this equation, you need to know. Your height is a function of time. The -16 talks about the force of gravity. This you will fill in a number, and this you will fill in a number. We tend to use t here instead of x because t represents time, and it's usually in seconds. If you're given feet per second, the time is in seconds. But if you're given something in miles per hour, the time would be in hours. But since we're talking about things going up in the air and coming back down, we focus on seconds. So let's take a look if we just change one of these values. If you look at all of our equations here, they all have the -16. Remember, that's the force of gravity. And I launched all of them from 5 feet above the ground. The only thing I changed is my initial velocity. For the red one, my initial velocity is just 10. So I threw it up and then it came back down in less than a second. But if I throw it up at an initial velocity of like 30, that's the green one here, it's in the air for over 2 seconds. And if I can throw something with an initial velocity of 50 feet per second, it's in the air for over 3 seconds. You can see that the parabolas get bigger and bigger, but they all have this y-intercept right here. That is how high it was above the ground. And it has an x-intercept wherever it crosses. Now how about if we keep the gravity the same, we keep the initial velocity the same, but this time we change the height at which it was launched. You can see a different thing happening here. All of these graphs look exactly the same, except they were just shifted up. So they stay in the air a little longer simply because they started higher. Not because they were thrown any faster, not because the curve is any more curvier, but just because it started higher, so it's going to take it a longer time to get back down. So let's say you have an object that's launched directly upward at 64 feet per second from a platform that's 80 feet high. Write the function for the height of this object at any given time. So remember, our formula that we're going to use is S of t equals -16t squared plus v naught times t plus s naught. So S of t equals our -16t squared. And really the only two things you have to fill in are initial velocity and initial height. So our initial velocity is 64 feet per second, and it started 80 feet high. So now we can ask some questions. When will the object reach its maximum height, and what will that maximum height be? So we know that this looks like a parabola. We know that something gets launched in the air and then comes back down. This point up here is max height. If I want to know when the object will reach this, what I'm looking for is my t value, or x value because it's on the x-axis. So I want to know the time, And what will the maximum height be is going to be the y value here, or the s value for s of t. So when you're asked this question, you're really asked to find the vertex. The x part of your vertex and the y part of your vertex mean totally different things. In this case, when will the object reach it is what it's asking, and how high will it be is this one here. So what we need to do is find our vertex. Now, before, we found our vertex by either factoring, completing the square, or a combination of those two things. I'm going to let you in on a little secret. You can find the vertex of something by using part of the quadratic formula. So in your vertex, you can find the x part of your vertex by using negative b divided by 2 times a, and then plugging that in to find y. Because remember, if you know an x value, you can always plug it in to find a y value. So remember, you have a, b, and c in your equation. So if it's asking you when the object will reach its maximum height, you're looking for x, which is the opposite of b, divided by 2 times a. So the opposite of 64 divided by 2 times negative 16 gives you negative 64 over negative 32, which is 2. So it will reach this at 2 seconds. And then what will that maximum height be? It's asking you how tall that's going to be. So what we need to do is plug in 2 seconds worth of time. So we have 2 squared plus 64 times 2 plus 80. And now if we had put this thing into vertex form, we would have figured this out already. But because we use this little shortcut here, we have to do some more math. So negative 16 times 4 gives us negative 64 plus 208. So if we do 208 minus 64, we end up with 144 feet. So if we look at a graph of this function, we graphed it here. We found this maximum height right here is at 144, and it happened at 2 seconds. Now there's a couple other questions that they can ask you. They can ask you how long it was in the air for. So if it starts here at 0 and then launches and takes until this time right here, this is our x-intercept, which is time in the air. This 80 right here is how high it started. So when this question says, when will the object reach its maximum height, what's it really asking? It's asking for x value in our vertex. And then what's the maximum height? It's asking for the y value in your vertex. So let's do one more problem. Let's say you have a baseball thrown straight up in the air, and its initial velocity is 29 feet per second from a point exactly 6 feet off the ground. Write a function for this. So remember, you keep the negative 16t squared the same. Your initial velocity has a t, and then 6 is your y-intercept, so that gets put on the end. When this asks when the object will return and hit the ground, we're asking for an x-intercept. So in order to find this x-intercept, we can do a couple of things. We need to remember that when this equals 0, our height is 0. So we have this quadratic function to solve, and we can solve this several different ways. We could look for something to factor, we could plug this in the quadratic formula, or we could complete the square. It's really up to you. Let's do quadratic formula. And the reason I chose that over completing the square is because if I have to factor out this negative 16, that's going to give me a really messy number right there. So my a value is negative 16, my b value is 29, and my c value is 6. So x equals the opposite of b, plus or minus the square root of b squared minus 4 times a times c, and it's all over 2 times a. So if we break out our calculators, we have the opposite of 29 plus or minus the square root of 29 squared, and then we have 4 times 16 times 6. And since there's 2 negatives in there, we're going to add these together, all divided by negative 32. So if we add what's inside our square root, we end up with 1,225 all over negative 32. And since we're graphing this, it doesn't really matter if it's a perfect square or not, but in this case it happens to be 35. So then this splits off into 2 problems. We have negative 29 plus 35 divided by negative 32, and negative 29 minus 35 divided by negative 32. So the first one, you end up with negative 0.1875, and the second one, 29 and 35 divided by 32, gives you 2. Now remember what we're solving for. We want to know when this object will return and hit the ground, so we're looking at time here. Now only one of these makes sense for time. We cannot have negative time. So 2 seconds is the one that makes sense with this problem. This right here is another x-intercept that is represented by this graph, but might not make sense for this function. So if we look at the graph of this, remember it started 6 feet in the ground, and then it took it 2 seconds to come back down. This is that other one that we found. Now, because this is real life, really the only part of the graph that we care about is from here to here and everything in here. But because this is a function modeled by a real life situation, it actually goes on forever and ever this way, even though it doesn't make sense in our problem. So whenever you get an x-intercept for projectile motion that's negative, it doesn't make sense in our problem. You just want the positive one. So you should be able to create and use a quadratic equation that models projectile motion to find maximum height, the time something's in the air, and how long it traveled. So let's say Jason jumped off a cliff into the ocean in Acapulco while vacationing with some friends. His initial height was 480 feet. His upward velocity was 16 feet per second. Write an equation and then answer those 3 questions. Make sure you write down any questions you have and we can go over them together in class. Enjoy your night.